This lesson is a little bit of a pause from the other lessons, which are like finding slopes of specific equations and maybe finding locations where you have certain slopes. Lesson 4 is very much like an other derivative question lesson. So you'll see some of the stuff we're doing here like looks different. A lot of the things do not have necessary applications. They're just like different types of problems you're going to see. We are starting off with equations where we're asked to find the slopes of. And these are our other trig functions like tangent, cotangent, secant, and cosecant. Now, we could spend time deriving the slopes of tangent by turning tangent into sine over cosine using the quotient rule, simplifying what we have. But you're not going to remember this. You don't have to do this because after we've done it once, we don't have to do it again. You just have to write down and unfortunately know for the future that the slopes of tangent are secant squared. Okay? We try not to memorize that much stuff in this class because there is stuff you have to memorize. So everything else try to understand, but you do have to memorize tangent's derivative is secant squared. I'll give this to you for next class and the future and the last class, but I won't give it to you for your test. Okay? Cotangent's derivative, very similar to tangent's derivative, but different. Similar to how sine's derivative and cosine's derivative are similar but different. One thing is very important is that a trig function squared like this, it can be written as secant of our value, quantity being squared. We'll do a practice problem where I'm asking you what is the slope of tangent at a certain value, and you'll have to find the secant of the value then square. If we did secant and cosecant, again, rewriting it and then using the quotient rule, we'd find that these slopes are secant x times tangent x. This is just something that you'll have to have memorized eventually. And I don't know, take a guess. What do you think cosecant derivatives are? That's fun to guess. Like we see the similarities with tangent and cotangent. Secant and cosecant will be similar. Take a guess. What do you think it's going to be? Yeah, here's what it is. Negative cosecant times cotangent. You guess wrong, who cares? Like, just trying it out. Some things that'll help you in the future. Noticing that cosine, cotangent, cosecant, their derivatives are all negative. So whenever you start with a C, your derivative will always be negative. Sine and cosine's derivatives similar. Tangent, cotangents are similar. Secant, cosecant are similar. So really, if you just remember one, hopefully you can figure out the other one. But that's up to you. Let's try to apply this knowledge. Please tell me, what is the equation that is tangent to the tangent function at pi over 4? Okay? Remember, we need our y minus y1 equals our m times x minus x1. We need some sort of slope equation to find m's. Plug in x's, get m's. Don't forget, plug in x's, get y's in your original equation. Go. We remember it as secant squared x If you move the square, make sure you have it as secant x quantity being squared. Don't plug in pi over 4 and square pi over 4. Like you find the secant of pi over 4 and then square it. Figure out what that is. You have to practice doing this. Like this is something I could have asked you in unit 0. What is the secant of pi over 4 squared? Close. Close. No, trying is key. If you don't try, you'll never know if you can or cannot do it. No. No, you're close. You did cosine. You squared cosine. You just need to flip this and you have secant. No, the squaring is the problem. Yeah, so, but you got 2. Nice, dude. You crushed the lesson, Jack. You crushed the lesson. You got to keep that into practice on the homework and then crush it. All right, so a lot of us did the cosine. A lot of us did the cosine of x squared. This is totally fine. The cosine of pi over 4 is root 2 over 2. I probably would flip this first and then square it, but you guys, I saw a lot of you square it first and got 2 over 4, which is 1 over 2. That would be the cosine of x squared. Flip it, you get the secant of x squared. Probably, I would instead get that the cosine of x is root 2 over 2. Flip that, 2 over root 2. Square, giving you 4 over 2, giving you that the slope is 2. We are experts at our unit circle because we took the unit 0 test. So we can do that. We know the tangent of pi over 4 is 1. So we got y minus 1 equals 2, x minus pi over 4. Okay? Secant is the reciprocal of cosine. You did the other one. Cotangent is tangent. Okay, let's move on. We're now into different derivative problems. Okay? Stuff that might not make sense but might be asked of you to do. For example, we have been taking equations and finding their slope equations. We have been taking derivatives, and though you guys don't like to write it, you should, especially for the last part of today's lesson, write that the derivative is f prime. This is not a 1, it's a little tick mark. This stands for the slopes of f. Cool? And none of you ever write the notation of the derivative of y, which uses this d over dx, and it's like the multiplication kind of idea, where you get dy over dx. But we should know that dy over dx is the same as f prime. It's the same as y prime. It just means the slopes of f, or the slopes of y. Cool? Well, sometimes, for fun, we might want to look at slopes of our slopes. So we might want to look at, now in unit 3, we will look at slopes of slopes a lot. We usually stop there though. In this unit, we will just be asked some questions that might call for you finding a second derivative. Now that is 2 tick marks, not an 11. It just means the slopes of my slopes of f. Every line is a tick mark. It's not a 1. This is not 11. This is just 2 tick marks. Yeah. Yeah, for now, for fun. In the future, there is use and value to a change of a change, to a slope of a slope. Okay? Cool. Now, over here, the notation using this d over dx turns into d times y, or d squared y, over dx times dx, which is dx quantity squared. They don't use the quantity and square it. They just write it as dx squared that way. Okay? They are like math books, and the AP test will be using this notation. Depending on the book you see, you might see different notation. Now, we can continue to add tick marks, but usually after 2, we stop using tick marks and we use numbers. So if I put a 3 there, I'm not saying take f to the 3rd power. I'm saying find the 3rd derivative. The slopes of the slopes of the slopes. Why? Because we can. We can. We will. You're about to. Okay, and it keeps going up from there. Now, so we will, yes, we will look at the graphs of f prime and f double prime and stuff like that. Okay, cool. Like, and Toda, you could do that. Do you remember how we sketched slope graphs? Could you sketch a slope graph of a slope graph? Yeah, sure. Now there's information from that actually tells you information about your original equation, which we'll get to. For right now, you're just going to have to be comfortable with handling a question like this, which asks for a 3rd derivative. But you're going to be careful. They're going to try to trick you. Let's see. Let's do this at x equals 1 so we get an easy answer to find. Ready, set, go. Can you give me the answer? I want the 3rd derivative. There's nothing fancy about 3rd derivatives or derivatives of derivatives. You're just going to need to take the derivative again and again and again and again until you get to the derivative you want. Okay? But make sure you understand what you have. We're plugging in 1. Let's plug in 1. So there is going to be a mistake that a lot of you will make, and that's okay because you're not paying attention. And it's just like, let's make this mistake now and not on our quiz, on our test. You'll see a question just like this on your test, guaranteed. Thank you. So I see a lot of us making that mistake. The answer is -6, not +6. The answer is -6. It's definitely not +6. And the mistake most people made is that you're not paying attention to what you're given. You are already given a 1st derivative. You are already given y prime. So you guys went to the 4th derivative. You took the derivative 3 times. That's good, but you only needed to take the derivative twice. You already had a 1st derivative. Here is the 2nd derivative. This is why notation matters, guys. And as we get later into this lesson, notation will for sure matter, and you'll have to be comfortable with notation. We are going to do notational derivatives. So you should write that this is the 2nd derivative. You should see that that's the 1st derivative. You should write that this is the 3rd derivative, either using tick marks or using the derivative notation dy over dx. You plug one into this, not into the fourth derivative to get -6. Now, the question is like the meaning, what does this mean? Don't worry about it. It's just a different type of derivative question, okay? Okay. I love this question because most people get this question wrong their first attempt. Here, I'll help you. I'll give you f prime because you didn't memorize it already. Did anybody remember what was the slopes of secant? Yes, secant x tangent x. Okay, cool. Well, then give me the second derivative, please. I do. I'm wondering if you got it. Yeah, you made the mistake. Yeah, Calc, you made the mistake. Don't worry, everybody makes a mistake. Oh, nice one, guys. Yeah, the slopes of tangent are secant squared. Slopes of tangent are secant squared. So the slopes of secant are secant tangent. Cool. Now I need to find the second derivative. The derivative of that. I love that idea that you wrote down, like where you're like, I need the slopes of secant. Yeah, that's great, but you have to do it. Very good. Good job.
Is that it?
Now, so here's we're gonna do another one too because it'll be on your quiz and on your test. Sometimes when you take a derivative, you won't use a rule. Like I just took the derivative of secant, I got secant x tangent x. But if I took the derivative of secant x tangent x, we have to notice that these are x's times x's. So all of a sudden, we have to use the product rule. I know, and everybody messes up on that, but this is why these are tricky derivative problems. So we have the slopes of secant again times tangent plus the slopes of tangent times secant. Slopes of secant are secant tangent. The slopes of tangent are secant squared. We end up with a lot of secants and tangents. If we'd like to, we could combine them to be a certain amount of secants or a certain amount of tangents. You could factor out a secant x if you'd like to. I don't think you need to. Okay. All right, you guys got space? Great. Towards the bottom, let's go second derivative of x sine x. X sine x, do this one. I'm giving you this one because it's going to be on your test, okay? Something just like that. Yeah, what's the second derivative of x sine x? Go for it. Again, why? Who cares? Just do it. You're going to have to take the derivative twice. Yeah, don't look back. The derivative of sine is cosine. You should know that. That's all you need to know. You don't have to look back anywhere. Go for it. Now, the first thing is you recognize this is a product of x's times x's, so product rule is where we should be starting. Ooh, that's a lot of confidence. Wait, so, okay.
Yeah, I'm going to draw this. Yeah.
Oh, you got it, yeah. You didn't show it. You did this in your head? You did the product rule in your head? All right, so some things to know, guys. This x is inside the cosine function. You cannot multiply this x by this x. If anything, you write it again with the x in front, and maybe you write the sine by itself. You don't know how to take the derivative of cos x squared anyways. We'll learn that next class. So once we get here, we should just take the derivative of sine. Cool. But then again, when you take the derivative of x cos x, you have to use the product rule. So if you did that, great. You're ready for that test question. What do we have? 2 of our cosine x's minus an x sine x. That is the second derivative of x sine x. Okay? So, like, we used the product rule. It created a sum. With my sum, I had to use the product rule for some of our sum. Like a little piece of my sum. I didn't have to use it here. Like tricky derivative rules. If you don't get it the first time, it's okay. These are tricky derivative rules. All right, we're going to skip the next one. We'll eventually do that more and more, but we're going to do my favorite one. The 43rd derivative of sine. We have plenty of time, so let's just start taking derivatives, and we'll eventually get there. Ready, set, go. Ready, set, go.
All right, so for the first
Come on. You have to start somewhere. What's the first derivative of sine? Okay, write it down. Write down cosine. That's the first one. Great. This will take the rest of the class, but it's okay. All right. What's the derivative of cosine? Okay, everybody write the second derivative. We're going to get to 43. Second derivative is negative sine, okay? And then negative sine's derivative. Okay, tell your neighbors, what's negative sine's derivative? Okay, cool. So we're at 2. Then the third one is negative cosine. Okay, let's keep going. What's the fourth derivative? What's the derivative of negative cosine? Positive sine. What's the fifth derivative? Okay, so do we have to write that the fifth derivative is cosine? Oh, what we realize is every time we take the fourth derivative, we're back to where we start. So this is the fourth derivative, the 8th derivative, the 12th derivative. Okay, now answer the question. Now answer the question.
Wow.
The 40th derivative, the 41st derivative, the 42nd derivative, the 43rd derivative. Okay? Guys, just heads up. If you're ever asked for like a very seemingly will take forever in a math class, there's usually some pattern that you can deduce and figure it out, okay? This one some of you could just think and get the right answer. What is it? 0 is right. Because I'll get a third, a second, a first, a constant, a 0, a 0. Okay? So sometimes you can think, sometimes you have to work out the pattern, but the sixth derivative of this is just 0. Cool. More interesting derivative problems. Differentiability. Being differentiable means having a tangent slope. There are two things that must be true so that you don't break Newton's marriage of a limit and a slope formula. The first thing that must be true to have a tangent slope is you have to be continuous at the location that you're looking at a slope for. If you don't have points, you won't have tangent slopes. Okay? So there's no tangent slopes at holes. There's no tangent slopes at jumps, asymptotes. The second thing that must be true so that you have a tangent slope is you can't have a sharp point. If your function somehow connects and creates a sharp point, there's no slope of this sharp point. It breaks Newton's marriage because to the left, just to the left of this point, we'll have slopes that are different than just to the right of the point. Sharp points are bad for tangent slopes. Now the way we are going to test you on this is bringing back our favorite guys, the piecewise functions. Because piecewise functions, again, this lesson is all about just different kind of derivative problems. Piecewise functions sometimes connect, sometimes don't. When they do connect, they typically connect at a sharp point. What we are going to do is we are going to find A and B, their numbers, so that our pieces not only connect, but when they connect in a smooth way so that the sharp point is gone. That will ensure we have slopes everywhere. Okay? So here's what we're going to do. I'm going to do one, you're going to do one. We got to make sure our pieces connect. That's the continuous part. That's the stuff you did in Unit 1. This is when you look at the limit, and you guys never write this down when you actually do the problems. When the limit to the left of 2, 2 being the important point where we leave 1 and start using the other, is equal to the limit to the right of 2. And we plug in 2 into the top, and we plug in 2 into the bottom, and we get 8a equals 4 plus b. This is something you've done. You did this for the Unit 1 test. But now we have something new that we have to ensure. When we connect, we do not connect sharply. We connect smoothly. We don't have a sharp point. Now, to ensure that, we want the slope of my first piece and the slope of my second piece to approach the same number, to equal the same number. We want the slopes to equal. We will look at the slopes to the left of 2, not just f, but the f primes. We will look at the slopes to the right of 2. Now, this is where it gets a little tricky and a little different. The slopes of ax cubed at 2. Well, a is a number the derivative of a number times x cubed. Think of like 5x cubed. The 5 doesn't disappear. You don't say it's 0. You don't use the product rule. You just bring the 3 down and multiply the 5, right? You say it's 15x squared. I am going to bring the 3 down, multiply it by a, and have 3ax squared. That's the slopes of the top piece. Don't forget, we're looking at the slopes of 2. I get 12a. Then we look at the slopes of the bottom piece. The bottom piece, x squared plus b. I'm going to challenge you because this is an important one. What would be the derivative of x squared plus b? 2x plus 0 for emphasis. You guys didn't say it. I'm writing it, though, for emphasis. Because b is just a number. So you think of x squared plus 7. The derivative of x squared plus 7 is just 2x. But don't forget that you're finding the slopes of 2. You'll be able to find one of your letters. You'll be able to then find your other letter. Boom. You will make sure that the pieces not only connect, but they will connect smoothly. So, summing things up, make sure your y's equal. Make sure your m's equal. Does that make sense? The y's equaling, the pieces will meet up. The m's equaling, they will meet up smoothly. The next one's a little tricky, so let's see if this one's going to be nice. Yeah, do this one. Go ahead. Your turn. I don't know if it works out nicely. But go. Find a and b to ensure that this function is differentiable everywhere. You read this differentiable and you're like, oh, okay, yep, this is when I have to check 2 things, that we meet up and that we have a smooth connection. Your y's have to equal, your m's have to equal. This one I think is easier than the other one we just did. Like you find A right off the bat. You just have to find B with a little bit of extra work. I don't think it's much extra work. Your Y's have to equal and your M's have to equal. That's really it. You have to connect and connect smoothly. You get A off of the Y's is 2. What'd you guys get B was? Come on, find B. You guys are slacking on the new stuff. Make sure we understand the new stuff. We got the Y's equal the Y's. Now ensure the M's equal the M's. Now. Yeah. It was too much on day 2. So I moved it to this. Yeah. Because it's A times x cubed. X is 2, 2 cubed, e. Making sure my pieces equal. The Y's equal to Y's. I plug 2 in to the X. Guys, get the M's. You have to get the M's of both pieces at 0. You have to take the derivative of the top piece. You have to take the derivative of the bottom piece and plug in 0. So I get a times negative sine x is the derivative of this piece. I get 2x minus b is the derivative of the second piece. A lot of people get stuck here, and they're like, what do I do now? But remember, you're connecting at 0. You want to make sure your slopes at 0 are the same. So you plug in 0 into your derivative. You get 0 equals b. b is 0. Like a weird one that works out that way. Cool. And there's more. More funky derivative questions. I'm going to replace the first one with a simple one. All right, everybody, write down this question in the middle. d dx for f of x, x equals 0. That is a question that I'd like the answer to. And the answer is a numerical answer. We will use our table or a graph for our information. We need to be okay with notation. These table problems are also like notational derivatives. You students hate notation and writing f prime and writing g prime and stuff like that. You just write the derivative of x cubed. You say 3x squared. But if I ask you what's the derivative of 4f of x at x equals 0, I need you to be able to get that it's 28. The answer is 28. How? Well, the derivative of a number times something, I don't have to use a product rule. I just have to say that the derivative of 4 times f of x is 4 times the derivative of f. You never write this down. Well, this is forcing you to do it. So thankfully it's here. This is the derivative of 4 f of x, 4 f prime of x. You then plug in 0, and you have 4 times f prime of 0. Oh, f prime of 0 is 7. 4 times 7 is my answer. Stop it, stop it, stop it. Would you take the derivative of 4 next to x squared and tell me that it's 0? Would you take the derivative of 4 next to sine x and tell me that it's 0? So don't do it here. It's not x's times x's. It's not a product rule problem. It is a constant that just gets left alone. The constant multiple rule. The 4 stays, the 2 comes down, gets multiplied by the 4. The 4 stays, multiplied by cosine. The 4 stays, you get multiplied by that derivative. Okay, so the one on the left, if I ask you, what is the derivative of 3f of x plus 2g of x at x equals 0, give me the answer. That's a g. This is 3f of x plus 2g of x at 0. I just replaced it so it's easier. (21) plus negative 8. 13. The answer is 13. Sorry.
I literally just followed the pattern. I don't understand. Okay, so you just used the prime, you ignored it. You used the wrong formula.
That.
I get it back.
Yeah, I got 13.
Now hold the phone. Don't feel too confident / oh, I figured it out. You just do this. 2f prime is the derivative of 3f. Sorry, 3f prime is the derivative of 3f. 2g prime is the derivative of 2g. You plug in 0, f prime of 0 we're told is 7, g prime of 0 we're told is 5. Boom, we get 13. Now we come over here to this one, and you all will get it wrong. You're all going to get it wrong. Why am I telling you you're going to get it wrong? Because none of you are going to be using the product rule. You all are just going to tell me it's 3f prime g prime. But no, guess what? These are x's times x's. So, yes, now Sahota, you have to take the derivative and you have to use the product rule and say, and we can talk about what to do with this 3. I like to bake it into the f. We get 3f prime g plus g prime, yes. We can either bake it in or leave it out, times 3f. That is the derivative you have to plug in 4. You'd have to do 3 times f prime of 4 times g of 4 plus g prime of 4 times 3 times f of 4. Yes, notational derivatives also have rules. Now let's look at the next page. Last thing. Yes, this is like 4 tricky different types of questions all coming at you. You will sometimes be given a graph. And maybe after you're doing your correct derivative rule, you're going to have to find f prime of 4. But it's like, where's my equation? What do I plug it into? Sorry, I'm just giving you the graph. But somebody here is going to tell me what f prime of 4 is. Look, you got it. You got to look. What's f prime of 4? -1 Lockmiller, and how'd you get it? F prime is the slope of f at 4. Guess what? Lockmiller looked at the slope of f at 4. So you will have to do that. It's a fun lesson, guys, isn't it? Hey, we'll see you next class. Hey, have a great weekend. Can't wait to do the homework video.